Alright. Okay. So in the video that I have attached in the e-learning, alright, it is about chapter 5, which is partial differential equation. Alright. So before this, what we have discussed earlier from chapter 1, it is about what? Chapter 1 discuss about first order differential equation. Chapter 2, second order differential equation. Chapter 3, still first and second, but only solve the differential equation by using Laplace. Okay, so all of those differential equation which were discussed earlier are from ordinary differential equation. Okay, and then we proceed with a Fourier series where we want to use that kind of Fourier series in this partial differential equation. So what is partial differential equation? Why it is differ to the previous differential equation that we have discussed? Okay, so we have to know that the differential equation, the partial differential equation, PDE itself, okay, is the differential equation is PDE when there is at least one partial derivative of u. Okay, let's say we have a function of u in terms of x and y, and then if there is at least one partial derivative of u in the given equation, then we call it as a partial differential equation. So, like there are examples of this PDE. Okay, we have wave, we have heat, we have Laplace. As you can see, there are partial derivative of u there. Okay, u is in terms of x and t. Okay, u is in terms of x and t. And there is ut prime, u double t, here is u double x. So there is at least one partial derivative inside the differential equation given. So we call it as a partial differential equation, right? So how can we find the solution of this partial differential equation? It is differ to the previous solution that we have discussed. Okay, we have in first order, we have to identify the types of differential equation. We solve it by using the types of differential equation approach for each of the types. Okay, and then in second order, we use characteristic equation. We identify the types of roots and so on. All right, so in PDE, what we're going to do in order to solve the PDE is to reduce. Okay, from PDE, we reduce to the ODE and then we proceed with finding the solution. So how? Okay, how can we find the solution for PDE? So the first one is by using the MSU method. Okay, I have shared with you about the MSU methods in the previous video. Okay, so this MSU method, of course, it is quite long, but the steps are there. Okay. Okay, let me share you. Can you see the screen?
Yes, sir.
Okay, so in MSU, right? Okay, we have this heat equation, right? We have this heat equation. As you can see, this heat equation is a function of u, comes from a function of u in terms of x and t. Okay, so in MSU, our first step is to identify what are the variables involved in the PDE given. So we have u, okay, u, we have x, we have t. So we expect, okay, we expect that our solution, so we assume that the expected solution should be in terms of u, x, and t. Why? Because we have u, x, and t there. Okay, we identify the independent variable, the dependent variable, and then we assume that the solution must be in terms of u, x, t. Okay, so let's say we have let's say here we have, okay, let's say here we have wave equation. Wave equation involve u, x, and t. So the expected solution should be u, x, t, x, and t. Okay.
This one, nice road.
And then we have Laplace. Laplace equation involve u, x, and y. So we expect that the solution should be x and y.
Okay. It's nice.
All right. Who's speaking there? Okay. So before we proceed with MSV, you need to understand that kind of problem will give the expected solution of what, right? So if you have heat equation where it involves u, x, and t, so we are going to expect our solution should be in terms of u, x, t, where it is a combination of function x and t. Okay, once you can have the assumption, all right, then we match to the PDE here. Okay, so for this example, we have here del u del t, k squared del squared u del x squared, right? Okay, then our solution, it is expected to be uxt equals to xxt. So in order to match with the PDE here, okay, as you can see, we have del u del t, where del u del t is ut. Del squared u del x squared, where it is u double x. We just differentiate this uxt according to the PDE. So you should have ut and u double x. So just differentiate xt here, ut becomes xt prime, u double x double prime t. Okay, and then once you obtain, then you just substitute to the heat equation. Okay, so the heat equation is given by del u del t equals to k squared del squared u del x squared. So del u del t is ut. So we have xt prime, k squared, x double prime t. Alright, so once you substitute, we need to rearrange accordingly to the variable. Okay, and then equal them to a constant of lambda. Okay, why? Because these two equations are equal when there exists a constant which makes them equal. Okay, so once you have equal them to lambda, then we can separate the function accordingly to each variable. So from this PDE, okay, from this PDE now, it is reduced to two equation of ODE. Okay, this is just a second order differential equation. This is just first order differential equation. Instead of this PDE now, we have these two ODE. Then by using MSV here, we are going to solve the PDE given based on the ODEs that you obtain. So this is the first step in solving the PDE. Is that clear, everyone? Okay, so I have discussed all of this in the video, and I'm not going to discuss again because for each example, the steps are equal. Okay, the solution steps are equal, so you need to understand how can you reduce first, okay, and then how can you find the solution. All right, so there are three types of, okay, there are three types of boundary condition. Okay, previously in the video, I have explained about the zero endpoints. Where you can see the condition is only involve u0t where x 0 here, ult where x equals to L, where it only involve uxt. But for insulated endpoint, it involve ux, where you have to differentiate uxt with respect to x. Okay, ux here, you need to differentiate u with respect to x. Okay, and then another one is mixed endpoints where the boundary condition involve u and also ux. So those are the difference. Okay, and the steps are all equal where we start with what? We start with reducing the PDE to ODE. Okay, and then once you obtain the ODE, we have to find the condition for ODE, and then we need to consider all cases of lambda because the ODEs that we obtain involve a constant value of lambda. So in order to identify the solution, we need to consider all cases for lambda, where lambda should equals to 0, greater than 0, and less than 0. Okay, and then once you obtain the solution for each cases, what we are going to do is to sum up all cases. So uxt case 1 plus case 2 plus case 3. If there is no interest for certain cases, then you just ignore them. Okay, just focus on the cases which give you the solution. Okay, so now let's try to do the second example, okay, of insulated endpoints. Okay, so same process, same steps, but only the difference is the boundary condition given for this case is insulated. As you can see, the previous example is 0 endpoint where its boundary condition only involve u and u. Then for insulated, the boundary condition involved with ux here. Okay, so how can we find the solution? Same process. Now, this is heat equation. Okay, this is heat equation where it involves u, x, and t. So we assume, okay, we assume that our expected solution should be uxt equals to a function of x and t. So uxt equals to x times t. So this is our expected solution. Okay, now in order to reduce this PDE to ODE, so first, our first step, reduce PDE to ODE by matching the expected solution with the PDE given. Now, this is your expected solution. Okay, and then in the PDE, we have del u del t, so you should have ut. So differentiate u here with respect to t, we have xt prime. And then we have del squared u del x squared, so you should have u double x. Then we differentiate u here with respect to x about twice. So we have x double prime t. And then substitute to the PDE. So this is your PDE. Okay. Del u del t equals to alpha squared del squared u del x squared. So substitute del u del t is your ut. Okay. Del squared u del x squared is u double x. And ut is xt prime. U double x is x double prime t. So now, rearrange, okay, and put the variable accordingly for each variable. So we have x double prime over x equals to t prime over alpha squared t. Okay, then these equations are equal when there exists a constant of lambda. So we can separate the function here for each of the variable equals to lambda. So this is x double prime over x equals to lambda, t prime over alpha squared t equals to lambda. So rearrange, then we can have these two equations as our ODE. So now this is ODE. We have this ODE. All right? Is that clear? Any question for this step? So this is our first step. We understand the heat equation, the PDE given. We identify the variable involved and we assume our expected solution, and then we match with the PDE given and substitute, rearrange so that we can have our ODE. So we reduce this PDE to ODE. So this is our first step. Any question? All clear? Understand or not? Other than Firdaus? Only one response?
Yes, doctor.
Okay. All right. And then we proceed with our second step. Okay. So we reduce the PDE to ODE. Okay. And remember, this is a problem involved with PDE. Of course, the condition here is for PDE. So now we reduce this PDE to ODE. So we have to modify the condition of this PDE. This is for PDE. Now we need to modify the condition to ODE. All right. Okay, remember, we have our expected solution, uxt equals to x, x and tt. Okay. And the given condition involve ux, where we differentiate u with respect to x. Okay, so this is the condition given for PDE. Okay, so in order to use this condition, you need to differentiate the expected solution, uxt here, with respect to x. So we have ux, where ux is x prime t. Okay, now matching with the first condition, ux0t equals to 0. Now uxt equals to x prime xt. So when x is 0, then here x is 0 equals to 0. So x prime 0, t equals to 0. Then putting this t to the right hand side will give you x prime 0 equals to 0. So this is the condition for ODE now. Okay, instead of this, now we substitute to this and we have this. Okay, and then another one, when x equals to L, then x here equals to L. So x prime L, t equals to 0. So putting t to the right hand side will give you x prime L equals to 0. So these are two conditions which are going to be used in the ODE here. Is that clear or not? So this is our second step. Okay, we're done with the first step, reduce to ODE. Second step, modifying the boundary condition so that it match with the ODE that we obtain. All right, clear guys? Anyone has question? If you have question, directly ask. Okay. It's going to be a long way until we reach our solution. So don't miss any misunderstanding. Okay, if you have question, you can ask. Okay, all clear? Now, let's move to the third condition. Okay, remember, we have obtained our ODE. So this is our ODE. Okay, this is our ODE. And in this ODE, it involves lambda, where this lambda is unknown. So our next step is to solve the ODE by considering all cases of lambda. So because the lambda here is unknown, then we need to consider all cases of lambda where lambda can either be 0 or greater than 0 or less than 0. So we need to always consider these three cases. Okay, so we start with lambda equals to 0. Okay, so for each cases, we'll give you different solution. That's why in our fourth step, we need to sum up all the solution obtained. Okay. Okay. The solution obtained from the first case, second case, and third case. So that's why we have to do it one by one for all cases of lambda. Okay, so start with lambda equals to 0. Okay, now this is your ODE. When lambda equals to 0, then, okay, we start with x first, with the first equation. First, from the first equation, when lambda equals to 0, we are going to have x double prime equals to 0. Okay, by characteristic equation, okay, remember in our second order, chapter 2, just change to the characteristic equation and understand the roots that you obtain. Okay, so x double prime now becomes m squared equals to 0. Will give you m1, m2 equals to 0. Why 2? Because square that. Okay, then we are going to have two roots. So this is real and equal. So, of course, if you have real and equal, the solution becomes EMX A plus BX. So remember, our expected solution should be X and T. So X, EMX, M now is 0, E to the power of 0, A plus BX. So X equals to A plus BX. So this is the general solution for X. Okay, and then once you obtain, remember our boundary condition. The boundary condition is x prime 0 equals to 0 and x prime L equals to 0. So this is x. So that's why we have to differentiate to find x prime. So x is A plus bx, then x prime is b. Okay, when x is 0, when x is 0, it is equals to 0, meaning that b equals to 0. Okay, so b equals to 0. Okay, when b equals to 0, then this x now becomes a. Okay, so when x equals to a, x prime equals to 0, x prime L equals to 0, where this condition does not affecting a, so the solution that you obtain should be x equals to a. Okay, for the previous problem, okay, for the previous problem, we consider case lambda equals to 0. You obtain x is 0. When a is 0, b is 0, x is 0. Then when x is 0, no point to find t because end up you will have x equals to u equals to 0. But now for this example, your x equals to a. There is a function of a constant here for x. Then we need to proceed with second equation. Remember, we have two ODE. So our second equation is t prime. Now lambda is 0. So t prime equals to 0. Change it to the characteristic equation will give you m equals to 0. So this is involve only one root. Okay. So, of course, it is not equal to anything. Then, if you have only one root, then we consider the cases of real and distinct, where it involves AE M1x plus BE M2x. So we only have one root, then we just consider this part. Okay, that's why T equals to CEMX, where M is 0, then T equals to C. So now case 1 give you x equals to A and T equals to C. And remember, our expected solution should always follow the PDE where it involves U in terms of x and T. So U equals to x times T. Now x is A, T is C. Where both are constant, then we just have a solution for case 1, uxt equals to D. Okay, just another constant. Is that clear for first case? Any question? Okay, no question. All good. All right. Now, that is for the first case. Then always proceed with the second case. Lambda greater than 0. Same process, just consider the cases of lambda. Now, second case, lambda greater than 0. So we choose p squared. Okay, every value, if we put square there, then it is always greater than 0, right? It is always positive. So we just assume that lambda equals to p squared for lambda greater than 0 and lambda equals to negative p squared for lambda less than 0. Okay, so now for the second case, lambda greater than 0, lambda equals to p squared. Substitute to the ODE here. Always comes to the ODE here. So from the first equation, now this lambda becomes p squared. Then we change to the characteristic equation. M squared minus p squared equals to 0. Then we have m equals to plus minus p, which are real and distinct. So we have x equals to aem1x plus bem2x. Then substitute m1 and m2 here with positive p and negative p. Okay, so this is your x. Okay, now this is your x, and in order to apply the condition, we have to have x prime, right? So we differentiate. This is your x. We differentiate. We give you x prime equals to px minus pbe minus px. So this one factorize. Put p outside. Okay, now apply the condition. When x equals to 0, x prime equals to 0. So substitute x here with 0. So becomes a minus b equals to 0. So PA minus B equals to 0. Put P to the right hand side will give you A minus B equals to 0. A equals to B. Okay, so when A equals to B, substitute again to X. Now, A and B here are same. Then just factorize the value of A. Okay, and then again, apply the second condition X prime L equals to 0. Okay, so x prime L equals to 0. When x equals to L, x here equals to L. It is equals to 0. Okay, so P here, this one, x prime. Okay, then put P outside to the right hand side equals to 0. Then put this to the right hand side will give you A equals to 0. Okay, when A equals to 0 and A equals to B will give you X equals to 0 because X involved with A and B here. Now, for second case, you obtain X is 0. Okay, and our expected solution should involve U, X, and T. And when X is 0, then there is no point to find T. So we put no interest in this case. That's why second solution for U give you 0 because this is 0 times with T also 0. Okay, is that clear? Any question? Take a look first. If you have question, you can ask. Anyone has question? Everything's good? All clear? Okay, good. All right, now proceed with the third case. Okay. So in our third case, where its lambda should less than 0, okay, so we use lambda equals to negative p squared. Okay, just substitute lambda here with negative p squared will give you x double prime plus p squared x equals to 0. Change it to the characteristic equation. We have m squared, p squared equals to 0. Will give you m equals to plus minus pi. So this is a complex root. Then you will have the solution of x equals to a cos px plus b sine px, where the value of alpha is 0, right? Because we should have what? Exponent alpha x, a cos beta x plus b sine beta x. So this is your beta b. Okay, now apply the condition. Okay, same process. Apply the condition. We have to have x prime. So we differentiate. We differentiate x will give you negative pa sine px plus eb cos px. Apply the condition x prime 0 equals to 0. So substitute x here with 0. Sine 0 is 0. Cos 0 is 1. So pb equals to 0. So from here, we can have b equals to 0. Okay. Now, second condition, when b equals to 0, just substitute b equals to 0. So your x prime will give you negative pa sine px. So when x equals to L, okay, when x equals to L, substitute L here, then negative pa sine pl equals to 0. Put this to the right hand side, will give you sine pl equals to 0. Okay, remember in Fourier series, sine and pi is 0. So these are equal. So PL equals to n pi, then P equals to n pi over L. Now you have your P equals to n pi over L. P is 0. Then your x here is a cos n pi x over L. So this is your x. Okay, for the third case, we have our x. Then we can proceed with finding t. So from the second equation, now your lambda is negative p squared. Substitute, give you t prime plus lambda squared, alpha squared p squared t. Change to the characteristic equation. Your m is negative alpha squared p squared. So this is only one root. Remember, if you only have one root, just use the real and distinct. Then we have here t equals to exponent m t. So m is negative alpha squared p squared and p is n pi over L. So just substitute n squared pi squared over L squared alpha squared t. So this is your, okay, and then this is your x, this is your t. Okay, then the third case give you the solution of u e a cos n pi L of x. This one, this is part x, and then this is part t. Okay, x times t. A is a constant, e is a constant, and it involves a sequence of n. Then we just have a constant of an. Okay, we simplify. We simplify a and e here with another constant a. Okay, we put n there because there involve a sequence of n, and pi here, n can be from 1 to 3 and so on. So that's why in our fourth step where we combine, now we want to have our uxt by superposition principle. We just combine all solutions from case 1, case 2 and case 3 to get our u. So case 1, u equals to d. Okay, so just put d there. Case 2, there is no interest because we got 0, then 0 there. Case 3 is here. So when it involves a sequence of n, then we just put a summation of n equals to 1 up to infinity of an cos n pi x over L exponent minus n pi alpha squared over LT. Okay, so this is a combination of u1, u2, and u3. So adding them together will give you this uxt. So this is the general solution of uxt. Is that clear or not? Just adding all solution for each cases of lambda equals to 0, lambda equals to lambda greater than 0, and lambda less than 0. Is that clear, everyone? Up to this point? Even though it's quite long, at least you understand the process. After this, you can try it by your own, and then you can have better understanding. Any question? So far, so good. Okay, up to step number 4. From 1 to 10, where are you guys? What we have been doing just now is to considering all cases of lambda, but still same step. Okay? All right, guys. From 1 to 10, where are you? Some got 6, some got 3, some got 5, some got 4. Okay. All right. Okay. Now you have done with finding uxt. Okay. But as you can see, there's still a constant involved there. So in order to find the value of constant there, we have to check, is there any condition is yet to use? Ada lagi tak? Okay. We have condition ux 0t. We have condition ux lt. Okay. Those are the boundary condition. And we have changed to the boundary condition used for ODE. Okay. But now we have done with finding uxt. And there are initial condition given. Okay, where ux0 equals to x. We have our uxt. Okay. And then we have another condition given ux0 equals to x, where t equals to 0 now. So before this, the condition involved the value of x. Now the condition involved the value of t. So as you can see here, this is the condition given ux0 equals to x, where t equals to 0. So you substitute t here with 0. So when t there equals to 0, then exponent to the power of 0 will give you 1. So when t equals to 0, okay, then ux0, d is d, right? an cos n pi x over L, an cos n pi x over L, exponent to the power of 0 is 1. So this is 1 equals to x. All right. So now, as you can see, this is a simplified version of uxt after we substitute t equals to 0. And this is a form of a Fourier cosine series where it involves cos. So as you can see, in Fourier cosine series, we have a naught over 2 plus summation of an cos n pi x over L equals to fx. And comparing these two, as you can see, this a naught over 2 equals to d. An equals to an. L equals to L and fx equals to x. So in order to find d, we can have a naught. We can find a naught. Okay, by Fourier series, all right, by Fourier series, a naught equals to 2 over L integrate from 0 to L fx, and your L is L. So L integrate from 0 to L, fx is x. Okay, integrate this will give you L. So A naught equals to L and D equals to A naught over 2. So D equals to L over 2. Now we have our D. Okay, and then AN. Okay, from the Fourier cosine, AN is given by 2 over L, integrate from 0 to L fx cos n pi x over L dx. So L is L. L here is L, fx here is x, L here is L. So by integration by part or tabular, integrate this will give you an. So once you obtain this an, just substitute to an here. Then this is your an, this is your a naught over 2. Then substitute to the function obtained in extension now. The constant of d and an is no more. So this is your final answer. Okay. Final answer is obtained when all conditions are fulfilled. All right. Understand or not? Any question? All clear? All right. So if you have taken a look at the previous example given in the video, the steps are equal. Okay, the difference is only on the boundary condition. So for the previous example, for 0 endpoint, when you want to apply the boundary condition, you don't have to differentiate. You just can use directly u there. Just substitute x0, x equals to 1. Then that is your boundary condition. Okay, then same process. And then for this case, it is insulated, so you have to differentiate. That is the only difference. Okay, then the process are similar. So once you obtain and fulfill all the condition, okay, and then you can have your final answer. All right, so I hope you can try to do it again by your own so that you can have better understanding. Okay, anyone has question? Only Li Zhuang clear here. How about the rest of you? Still consuming? I'm not saying this is easy, okay, but you have to try to do it again and familiarize with the steps, right? And then you can have better understanding. Okay, of course you need to revise again. Okay, so we have done with the first example and second example. Yes, of course, I'm going to upload this video because this is today's class is second example, right? In the previous video, that one was first example. Okay. Alright, so I'm not going to proceed with the next example. I hope you can try it one by one with the previous example for 0 endpoints and today's example for insulated endpoints. After this, we can proceed with the next example in our next class, right? Because this is quite long, I'm not going to mix your understanding. So please make sure you understand very well first before we can proceed with the next example. Okay? Anyone has question before I stop? And I'm going to leave you with this example for you to do it by your own. All right, so remember tomorrow is our second test. Chapter 2, excluding the application, right? Starting after test 1 topic. And then chapter 3, up to inverse, excluding convolution onwards. So no solution of IVP, BVP, and system of differential equation by Laplace. So I think it is clear enough from the information given, shared in the group, right? If you have problem, you can ask. Okay? Okay? Okay, everyone? So far, so good? Test 1. I'm sorry, I'm not finished yet. Perhaps before your final, before study week. Okay? All right. So if you have no more questions, you can end our class with Suratul As and Tasbih Kifarah for Muslim. And don't forget to scan your attendance here.